All right. So begins the Galois theory. As you know, you've got a test on like chapter 13, which you'll do sometime next week. But the next story arc in this course is essentially chapter 14 of Dummett and Foote. Of course, as always, we will not cover all of it, but we'll cover a good chunk. And at times, I'll also refer or rely on some blurbs, as they're known, by Keith Conrad. This is the Galois correspondence. I posted it in course content. He has some notation in here, which is helpful, which I don't think is in Dummett and Foote. And he also he tends to have like the same examples as Dummett and Foote, but with a little more details. So it is very helpful at points to know about that. But I'm going to try to stick to Dummett and Foote here for the moment, and see where it takes us. So, definition. An isomorphism of sigma from a field to itself is an automorphism of K. So an automorphism is a isomorphism from something to itself, right? And all such are in all automorphisms of K is ought K, all right? First point. Second, if sigma in the automorphisms of K, right, has sigma of alpha equal to alpha again, all right, for some alpha in K, then sigma is said to fix alpha, right? And by the way, he doesn't always write the parentheses. So sometimes this right here will instead just write sigma alpha equal to alpha. So just forego the parentheses in that at times. All right. And he says, if F is a subset of K and the automorphism fixes every element of F, then it's said to be a F fixing, or said to fix F, right? So that we can extend this idea to subsets. So likewise, if F is a subset of K and, sigma alpha equal to alpha for all alpha in F, then sigma fixes F, all right? At this point, he points out that every field has at least one automorphism, the identity map, which we'll denote by 1, and that's sometimes called the trivial automorphism. Let's see here. He also mentions the prime field of K is generated by 1, right? And so let's think through this. So if, sigma is an automorphism of K, right? And let's say F is the prime subfield of K. What's that mean? So that means F is either up to isomorphism the rational numbers, if it's a characteristic zero field, or it is, you know, the finite field of characteristic P, right? Those are your choices for prime subfield, right? But anyway, is F fixed by an automorphism? Well, then by definition, right, sigma of 1 equals to 1. But also, what can we do with 1? We can add it repeatedly or subtract it repeatedly. We can build the integers or the integers mod p, right? And then you can look at the field of fractions of that. That's also a subset of the field, right? So in short, this implies that sigma of alpha equals to alpha for all alpha in the prime subfield, right? In other words, any automorphism automatically fixes the prime subfield, right? So the prime subfield is fixed by every automorphism. That's just from the definition of automorphism. All right. And what does that mean, by the way? What does that say about automorphisms of prime subfields, you know? What are the automorphisms of the rationals, right? What are the automorphisms of, well, he tends to use F sub p. We previously have used Z sub p for that set, but I'll try to stick with Dummett and foot notation, the finite field of characteristic P, right? So what did we just say? We said any automorphism fixes the prime subfield, right? So what does that mean if any automorphism, so like sigma was arbitrary in the remark above, right? And we just showed that sigma of alpha equals to alpha for all alpha in either F equal to Q or F equal to FP. So there's only one automorphism, and it's the identity automorphism. So these are just equal to. Now remember that the automorphism, set of automorphisms forms a group under function composition, right? You remember the homework I gave you last semester on that? Maybe. I think I do. Yeah. All right, so next definition. Here we go. Let K over F be an extension of fields. Extension of fields. And then we're going to define ought K over F to be equal to sigma in the automorphisms of K, such that sigma of alpha equals to alpha for all alpha in F. In other words, ought K over F, these are the F-fixing automorphisms of K. All right. So there's always at least the identity map in there, right? And in fact, you can prove that this is a, you know, like for a stupid comment, you know, if you look at ought Q over Q or ought FP over FP, it's just equal to 1, right? I mean, as an application of this notation in the most silly case possible, here's one, right? Q over Q, very silly. You know, FP over FP. I mean, any field is an extension over itself, right? And so, yeah, stupid, but anyway, there it is. What's more interesting, though, is the following proposition. Prop 1. Excuse me. Ought is group under composition and the F fixing automorphisms of K is a subgroup of K. Yeah. His proof begins with, it's clear that aught K is a group. Okay. Is it clear that aught K is a group? I mean, I think it is for people who, it depends on your background, right? So I think it's worth our time to just spend a second to prove that aught K is a group, right? So aught K is a set of isomorphisms from K to itself, right? So why is aught K a group? Note, if we have sigma, alpha, beta in aught K, right? Then sigma composed with alpha, well, let's not write the composed symbol. Let's say sigma alpha beta is equal to sigma alpha beta. What I'm saying is you can put the parentheses either way. In other words, why is this true? Because function composition is what? Associative, right? Right. And sigma, alpha, and beta are all functions from K to K. Let one of x equal to x for all, K, then you can prove one. Well, of course, one maps 1 to 1, and 1 of x plus y is what? X plus y, 1x plus 1 of y, right? And 1 of xy is equal to 1 is equal to xy is equal to 1 of x, 1 of y. And of course, it is its own inverse, right? So it is indeed a isomorphism from K to K, right? Just the identity map, which I'm calling 1. All right, so my claim is that serves as this identity map serves as the inverse with respect to composition, right? So to show it's a group, we need to show it has an associative operation with identity. The identity is the identity map, which I'm calling 1. And what else do I need to show? Right.
That you showed composition, you showed multiplication. You have to show.
Let's segment alpha. Yeah, go on. If we can show that it's closed under composition, right? We need to show that the composite of two isomorphisms is again an isomorphism, and we also need to show that it's closed under inverse, right?
Yeah.
So, and once we have those, then we'll have all 4 things we need for it to be a group, right? Associative, has identity, closed
Inverse.
inverses, right, under inversion. So if sigma and alpha are in K, and we look at sigma alpha of, x plus y, we get sigma of alpha of x plus alpha of y, using the alpha as a isomorphism, which is then sigma alpha of x plus sigma alpha of y, using that sigma is a homomorphism. So there you have it. Sigma alpha is additive, right? And multiplicative is very similar. Right, which is sigma alpha of x, sigma alpha of y. Anyway, so we have multiplicativity of the map. It preserves multiplication, it preserves addition, and of course, the fact that it sends one to one, the both of these send one to one is also like clear, right? If you'll forgive me for not writing it down, I'm not going to write it down. So therefore, thus, sigma alpha is an automorphism, right? And then, okay, so then what? We still need to prove it's closed under inverse. How do I know that the inverse of an automorphism is an automorphism?
Isomorphisms have inverses that are bijections, don't they?
Right, so let sigma be an automorphism of K, then what?
And it's an automorphism of that too.
Right, then sigma goes from K to K. What can we say about it? It's a what? It's a one-to-one map, right? It's bijection, right? Hence, sigma inverse from K to K exists, right? Right? So first of all, it is an invertible map, but it still remains to show that sigma inverse is in fact a automorphism, right? How do we show that? Well, yeah.
We have it from the ridiculous.
So let x and y.
We have to show sigma inverses.
Right. So yeah, let.
But it's still not from K to K. You just go from the domain, codomain to the domain. And if those two are equal, then don't you just get automatic?
So how do you get additivity for that? If it's automatic, it should be easy to explain.
So we're saying sigma inverse is a mapping from K to K.
Mm-hmm.
And so all you have to say is that's equal to sigma inverse x plus sigma inverse y.
But that's assuming what we're trying to prove. But I think you're on the right track. This is sigma inverse of sigma inverse of x plus sigma of sigma inverse of y.
It's the biggest proof I've ever seen.
But I know that sigma's additive.
Yep. I see where you're going, and I'm just like, that was a complete waste of time. But I understand why you have to do it. Sigma.
But then this and that just gives me that again, by definition of inverse. So what I'm really exploiting here is that sigma is surjective. So I can recast any element of K as the image of another element of K under sigma. And that other element is sigma inverse of x, as it happens. And a similar argument shows that likewise, right? Once you see this, you know that you can do the other one, right? I mean,
Yeah.
by essentially the same song and dance I just did here, exploiting the multiplicativity of sigma transfers to multiplicativity of sigma inverse. And then the fact that sigma sends 1 to 1 immediately tells me that sigma inverse sends 1 back to 1, because it's just the reverse of the sigma map. So anyway, therefore, sigma inverse is an automorphism of K, but it's also arbitrary. So we have shown that aut K is indeed a group under composition because it satisfies the group axioms with respect to the construction of function composition. Now, I don't usually prove this inside Abstract 2. Like, my usual curriculum is that's part of my Abstract 1 course, and you kind of see why, right? Because it's like, this is a natural extension of the discussion of like just of isomorphisms of groups and stuff, but I'm pretty sure you haven't seen it, so I thought it was important to go through. And it's not hard, right? But there is something, it's not hard, but there is something to say here, right? I mean, now the second part of the proposition is genuinely new stuff. Why is it that the F-fixing automorphisms of K form a subgroup of aut K? How shall we prove that? Let's see here. So proof of F-fixing automorphisms of K is a subgroup of aut K. It's a subgroup, so we got our choices. What kind of subgroup test do you want to try? I'm going to prove it's non-empty, right? So like note 1 equal to the identity on K, right, is an element of the F-fixing automorphisms of K. That is clear. The identity fixes everything, so of course it fixes F. Okay? All right, so let's let sigma and alpha be elements of, although he tends to use alpha for an element of something. I should stop using alpha for, I need to stop, I gotten in this habit so far of this lecture of using alpha for an isomorphism. I really should not be doing that. He tends to use alpha for an element, and he uses sigma and like sigma, beta, tau for isomorphisms. Let me try to maintain that habit as to not confuse the notation. So let's let sigma and tau be F-fixing automorphisms, okay, all right? And let's let alpha be an element of F, right? Check this out. So if I have sigma, tau, right, that element, acting on alpha, what happens? We get sigma of tau of alpha, right? So I'm putting parentheses in just for, because we're used to parentheses. But he might omit them. Anyway, the point is tau alpha is just alpha, right? Because, again, tau is a F-fixing automorphisms, okay, right? So tau fixes alpha. And what does sigma do? Well, it fixes alpha, right? So what does the composite of sigma and tau do? It fixes alpha, right? So, and that, since alpha is arbitrary, implies that sigma tau is a F-fixing automorphism of K, right? Now what else do we need to check? If we check, I'm going to do the two-step, basically non-empty and then closed under composition, closed under inversion, right? So I'd like to also show that sigma inverse fixes F. Now I have at least one time I was teaching this course, I got terribly hung up on this. I don't even know how I got so hung up on this, but I got really hung up on this. So like sigma inverse of alpha, right? Again, for alpha and f. How do I show that's fixed? What do I do here? How am I going to prove sigma inverse of alpha is equal to alpha? What should I do? We're still assuming that sigma is a f-fixing automorphism of K, okay? Yeah, I think if you see it, you'll see it right away. If you don't see it, you know, like, you can stare at it and stare at it. But once I write it, you'll just be like, oh, well, duh. Right?
See, but
We know.
but that doesn't prove.
That doesn't prove yet, no, but that's true. That's something that's true.
Yeah, I got that part, but I'm trying. I'm like everything gives you alpha again.
That's right. So this gives us alpha again. That's what we're trying to prove.
Yeah.
That sigma inverse fixes alpha. See, it sends alpha to alpha. That's what we're trying to show. So therefore, sigma inverse is an element of the f-fixing automorphisms of K. And that completes the proof because we've shown closure under composition and inverse, and it's non-empty, so by the subgroup test, aught K over F is a subgroup of aught K. Now, I mean, this is fun and all, but why are we even talking about this stuff? Like, why is this interesting? This starts to be interesting. You start to see why it's interesting as we look at Proposition 2. Proposition 2 starts to sort of show you why we're looking at this stuff. It's because these automorphisms have something to do with roots of polynomial equations. And that's, I don't think that's, like, obvious yet, right? So the interesting thing about all this stuff is, you know, this was, Galois invented group theory for the sake of solving a problem.
I didn't know.
It can be argued that. I think he's one of the first people who really had, I mean, so many different things are a group, right? So you could go and you'd be like, well, such and so forth in antiquity studied blah, and we know that's a group, so he was a group theorist, right? But Galois is one of the first people who not only defined something which had the structure of a group, but he also used group theoretic properties to study how that thing interacts and solves his problem. He was like the first practitioner of using group theory to really solve something.
What was his time frame?
He lived 1811 to 1832. If you subtract those two numbers, what do you get?
11 to 17.
No, 1832. He died in 1832. He was born in 1811.
He was
22, yeah. Died in a duel.
No, really?
Yes. I believe. French, no less. Let's see your Proposition 2. Let's see here, and he kind of had a sense that he was going to die, possibly in this duel, so he like feverishly wrote down all the mathematics he was thinking about, like the day or whatever beforehand, and most of his work wasn't really appreciated until sometime after his death. Let's see here, K over F be a field extension. I believe that's true. Anyway, if it's not true, let me know. K over F be most likely a woman. Field extension, I don't really know. It could have been politics, I forget. Field extension. And let alpha be alpha an element of K be algebraic over F, all right? Then for any F-fixing automorphism of K, any sigma, an element of K over F, all right? Sigma alpha is a root of the minimal polynomial for alpha over F. In other words, the F-fixing automorphisms of K permute the roots of irreducible polynomials permute the roots of irreducible polynomials. And what else can we say? Equivalently, for any polynomial with coefficients in F having alpha as a root also has sigma alpha as a root. Getting tired.
He happened to be born during the French Revolution.
Hmm.
So most people are prepared from school too. He was a staunch Republican, as Wikipedia has put it.
He's a staunch Republican. I'm not sure that even makes sense. But he's a mathematician, so he's kind of logical, so I hear what you're saying. Sorry. I think it's probably a dangerous game to try to find logic in any political party. But it's hard for
Right after his release from prison.
hard for logic to find anything. Hard for logic to pry anything away from the cold, dying hands of pragmatism. But anyway, so let's see. He was what?
Like he went into this duel right after he got released from prison.
He was in prison, then he went to the duel.
Yeah.
Okay.
So he probably did all this while he was in prison.
Again, good prison math. Yeah. It's kind of funny you bring that up because the other place where group theory could be arguably invented is in the study of transformation groups. So that's the kind of stuff you've seen in your special relativity course, like the Galilean transformations, but like more generally, coordinate transformations form some kind of group.
Yeah.
And so if you're studying differential equations, you might want to change coordinates to be able to solve the problem.
Yeah.
So people who were trying to solve differential equations through inventive substitutions also found their way to groups. And that was more the...
Makes sense though, because we know the dihedral groups.
Mm-hmm.
So these are just flips and stuff.
Right. Yeah. The dihedral groups, like these the finite groups, which appear as symmetries of plane geometry. Sure. But yeah, Klein and Lee and Klein, like Sophius Lee of Lie algebras, Lie groups. I'm trying to remember which one.
There's also topologists that
One of these two. I think it was I can't remember if it was Lee or if it was Klein. Curses, my bad. But one of these two was he looked rather foreign, and he was walking somewhere in wartime, and he got picked up because they thought he was a spy, and he languished in a jail for like a month while he did very good mathematics. And then eventually somebody from some university was like, hey, he's not a spy. Let him go. But
5 days before his death, he wrote a letter to Chevalier, which clearly alludes to a broken love affair.
yes, I have a song about that I can share with you.
As long as you don't sing it.
I'm not going to sing it, but I will make you listen to it. It is it's a beautiful work of mathematical fiction. But anyway, and it's the ballad of Stephanie, I think. I'm trying to remember. Anyway, I will send you a link. Okay, so proof. How shall we prove this assertion? So you remember our notation before for minimal polynomial was what? It was like m alpha of x, right?
Yes.
And sometimes we did m alpha over f of x if we were feeling very pedantic. And you remember the prop 9 said what? It said that if f of alpha equal to 0, then m alpha of x divides f of x. Remember that? That's another thing we know. Like anytime you have, if you have a polynomial which takes alpha as 0, the minimal polynomial must divide that thing. Okay, these things we know. All right, so what are we supposed to prove here? The alpha be algebraic over f. All right. Then for any sigma all right, let's see here.
Well, we got to split a polynomial.
Oh, he's like, so he starts with, suppose that alpha satisfies an equation, right? So that's his starting point. We have alpha to the n plus alpha a sub n minus 1, alpha to the n minus 1 plus a2 alpha squared plus a1 alpha plus a0 equals to 0 for somewhat selection of coefficients, right? In where? In f, right? Because we're assuming it's algebraic over f, so there's some polynomial in f, which when you plug it in, you get 0, right? And without loss of generality, we can take that to be a monic polynomial, as I have there. All right. Okay, so at the moment, he's just, what's he doing? We're actually starting, I think he's actually picking on the last sentence first, right? So we're letting f of x be what?
Like be split by alpha, or be root, the polynomial that alpha solves that takes root 0.
Right. So I mean, if you'll forgive me for squeezing something in here, we're letting f of x equal x to the n plus plus a1 x plus a0 with f of alpha equals to 0, thus there, right? Now what's our goal? Our goal is to show that f of sigma alpha is also equal to 0, right? So let sigma be element of k over f, right? Let sigma be an f-fixing automorphism of k.
Well, we know that we have
Mm-hmm.
that sigma alpha, f of sigma alpha is also
Let's see here.
are we trying to prove that?
Well, I think, yeah, we're trying to prove that. So what we're going to do is we're going to take this equation right here, I'm going to call it star, and we're just going to act on star by sigma. You know, from star, we get 0. I said 0, but I wrote sigma because I'm an idiot. 0 is equal to sigma of alpha to the n. And if you don't mind, I'm going to use the additivity. I'll start, my opening move will be additivity of sigma, right? So this is by additivity, which of course, if you have additivity for two things, by induction, you can make it work for, you know, n things, right? But we also know that sigma is a homomorphism, right? So that means that sigma of alpha to the n is sigma of alpha to the n, right? Like that. See, sigma of alpha to the n is sigma of alpha to the n.
Star and star equaling each other.
So from star,
No, look.
act by sigma.
Look at your second term, alpha an to, sorry,
An minus 1, yeah. Thank you. My bad.
Should that be an now? That's the first coefficient.
You can label them however you like. I just made the index match the power. Then we have sigma of an minus 1, sigma of alpha to the n minus 1. So I'm using the fact that, you know, if we have an isomorphism acting on x and we raise it to the n power, or rather on x to the n. Try this again. If I have an isomorphism acting on x and I raise it to the n power, that is this as well. Although I'm using it backwards, so like this is equal to that. Because, like, you know, for example, phi of x squared is phi of xx is phi of x is phi of x squared. And then you can inductively extend that. We did this the other day. So what do we got here? Plus plus sigma of a2, sigma of alpha squared, sigma of a1, sigma of alpha, plus sigma of a naught. Now, up to this point, I have not even used the fact that sigma is an F-fixing automorphism of K. I've just used that it's an automorphism in the calculation thus far.
Yeah, but really what we need to get to is the coefficients.
Mm-hmm. So let's see here. This one stays the same, but can you tell me if sigma fixes F, a sub n minus 1, a sub n minus 2, all the way down, all of the coefficients of the polynomial are from F.
Yeah.
They're fixed by alpha. That means, sigma. That means that sigma of n minus 1 is a n minus 1. And at this point, I'm getting tired. I'm just going to write it sigma alpha to the n minus 1. Do you see why he didn't write the parentheses? A2, sigma alpha squared, A1, sigma alpha plus A0. But that is precisely what? That is precisely F of sigma alpha. I think it's interesting to notice that even if the automorphism is not F-fixing, this calculation still says something, right? It still says that if you take a root of f and you map it under, you map it under an isomorphism, you do get sigma alpha is a root of another polynomial equation. It just has possibly different coefficients, right?
Yeah, but the other thing is
This is actually a theorem we had earlier. But
alpha's in K.
alpha's in K?
Yeah.
Oh, this is true.
So why does sigma fix alpha if it's in K?
Sigma, yeah, well, sigma does,
Automorphism of.
sigma does not fix alpha. Sigma fixes the coefficients of the equation, which make alpha algebraic. Yeah, sigma does. Sigma. We did not say sigma fixed alpha. We only used this property for like x equal to alpha, so to speak. So at this point, we've proved the last sentence here, and so permutes the roots of irreducible polynomials. I think that's like immediately true from this calculation, because if you have an irreducible polynomial, right? If you have if f is irreducible, right? And f of alpha is equal to 0, then f of sigma alpha is equal to 0. So sigma alpha is root. I'm really not saying anything. I'm just saying that this equation being generally true, it's still true in the case of an irreducible polynomial, right? We did not assume irreducibility of f here at all.
That's weird, though.
And what does it mean to permute? It just means it's sending one root to another root, right?
Yeah.
And what's the previous sentence? For any sigma alpha is a root of the minimal polynomial of alpha over f. Now, how do we know sigma alpha is a root of the?
We assume the minimal polynomial start.
Let me just think. I don't think there's, right. So if we know what we know that alpha is a 0 of the minimal polynomial, right? So m alpha over f, right, of alpha is 0. So taking the case, again, the same calculation, putting f equal to the minimal polynomial of alpha implies m So, I mean, in some sense, I think proposition 2 is most interestingly stated simply as the last sentence in it.
Yeah.
But the first two sentences are really pedagogical.
Yeah.
What he's trying to do is, when he's referring to Prop 2 in future use, it's the first two sentences which we always find ourselves using. But the general result is actually the third sentence, which we proved. You know, it's not about the irreducibility or the fact that it's minimal. It's just a case that the f-fixing automorphisms of K permute roots of algebraic. They permute the roots of polynomials over f. Yeah. Mm-hmm. So.
Sigma's a map that's mapping alpha, but it maps alpha to alpha. So.
Yeah. Let's see here. Let me break from Dummett and Foote here momentarily. And let's figure out what are the automorphisms of complex numbers. Because I think it's useful. What are the automorphisms of the complex numbers which fix the reals? So what are we looking for? We're looking for a sigma, right? From the complexes to the complexes, such that sigma of x equals to x for all x in the reals, right? Which we're viewing as a subset of the complex numbers. So, what does that look like? Let's see here. He says, so here, this is from the start of the blurb by Conrad, actually. But I think it's like a nice little calculation. I think it helps give us a little bit more confidence about what are automorphisms, you know? Okay, so sigma of a plus bi, all right? Usual complex variables rules apply, a and b are real. So this has got to be sigma of a plus, you know, sigma of ib by additivity, right? But because if sigma is R fixing, right? Of course, you can also, one more, this is sigma of A plus sigma of I, sigma of B, right? But it's R fixing, right? So that has to be A plus B sigma of I.
Yeah.
But what else do we know? So what are the possible R fixing automorphisms of C?
Anything that takes a to any real number and b to 0.
What can we say about sigma of I? Like, what can sigma of I be? Is that, can we make that just anything we want? I mean, what are we, there is strings attached to I, right?
Yeah.
So
I squared is a real number.
I squared is -1, very good. And so that means that sigma of I is sigma of -1, right, which is -1. So in other words, we have sigma of I quantity squared is equal to -1. What are the solutions to that equation?
X plus I minus 1.
No, sigma of I equals what or what? How can you get sigma of I squared being -1?
It's equal to I or minus 1.
Right. You got it. Exactly that. Plus or minus I. So those are the. That's it. I mean that's it. So basically we either have sigma plus, you know, or we have sigma minus. Of course, if you put this in the complex notation, perhaps it's more familiar. We have sigma plus of z equals to z. We have sigma minus of z equals to z conjugate.
Yeah. I understand, like, why.
So the automorphisms of the complex numbers, which fix the real number field, subfield, there are just two of them, either the identity map or complex conjugation. So in fact, complex conjugation is really our first example of what's called a Galois conjugate. Which we'll define more carefully here in a minute. But all right. And you can easily see that this form, what's the group? As a group, what is aught C over R? It's a two-element group, right? It's got 1 and, you know, sigma minus, if you will, right? There's only one group with 2 elements, right? It's the finite group of order 2. You look at isomorphism, it's Z mod 2, you know? All right. So let's see here, going back to the Dummett and the foot. I like this calculation. It's very clean and understandable, and it says something really interesting, you know. The only automorphisms, R-fixing automorphisms of the complexes are, the only non-trivial one is complex conjugation. So examples. This is from page 559 of section 14.1, thumb it and foot. Third edition, of course. Let's see here. He's like, let K be Q adjoin square root of 2, right? And he says if tau is an element of ought Q join square root of 2, right? Then tau of square root of 2 has to be what? Yeah, the thing I just erased said that. So, you know, this is the thing I just erased applies because remember, ought, I'll write it up here. Ought Q, so ought Q over root 2 is the Q fixing automorphisms, right? Because it's, all right, so the theorem applies.
Oh, I was using this over here.
It is related, but what I'm trying to say is the minimal polynomial for the square root of 2 over the rationals.
Yeah, is x squared minus 2.
Right. So x. Okay. So that has two solutions, right?
Yeah.
So there are two roots. See, we could send square root of 2 to plus 2, plus root 2, or to minus root 2. So that means that tau of a plus, b root 2 could be a plus or minus b root 2 because tau fixes q, right? So the a and the b pop out unscathed by tau. And root 2 is either sent to root 2 or sent to minus root 2. So again, you get that the ought k here actually is again 1 and tau. Let's say tau minus. Just use my silly notation again. All right. All right, now, second example, a little bit more festive. So now we've got k equal to q adjoin the cube root of 2. All right? And we'll say if tau is an element of ought k over q, then what?
Same song and dance.
So let's see here.
Actually, no, it's not. It's 3. But you just do the minimal polynomial of root 3 of 2 over q of x equal to x cubed minus 2.
Well, I guess the question is, so then tau is, of course, a mapping from where to where, from k to k, right?
Yep.
What does k look like? What's a typical element of k?
Any rational number you find.
Right? Irrational a plus b times cube root 2, right?
Yeah.
Plus c times cube root 2 squared, right?